Welcome back everyone in the lecture 17. We now explore the spectral information obtained using advanced spectrofluorometers. We will also begin examining the specialized hardware requirement to measure extremely faint luminescent signals. When operating spectrofluorometer, we generate two fundamental spectra, the excitation spectrum and the emission spectrum. First, the excitation spectrum, its purpose is simple, to identify which wavelengths are most efficiently absorbed to produce fluorescence. How do we measure this? We fix the emission monochromator at one wavelength, usually the wavelength of maximum fluorescence. Then we scan the excitation monochromator across many incoming wavelengths. We plot the fluorescent intensity versus excitation wavelength. After instrument correction, this curve closely resembles the visible absorption spectrum. This is extremely important. It tells us the optimal pumping wavelength for maximum luminescence efficiency. Now consider the emission spectrum. Here we reverse the process. We fix the excitation wavelength at an effective pumping value and scan the emission monochromator across longer wavelengths. The emission spectrum reveals internal electronic transitions, vibrational energy spacing and energy band structure. For physicists and chemists, this becomes the primary tool for studying quantized energy gaps in molecular systems. Let us now examine a real experimental example. Shown here are fluorescent spectra for 1 part per million solution of anthracene in alcohol. Curve A is the excitation spectrum and curve B is the emission spectrum. Notice something remarkable. The emission spectrum appears almost like mirror reflection of the excitation spectrum. This phenomenon is called mirror image rule. It arises directly from the Franck-Condon principle. The vibrational energy spacings in the ground state S0 are very similar to those in the excited state S1. Upward absorption transitions and downward emission transitions follow matching vibrational patterns. As a result, the macroscopic spectra appear strictly symmetrical. Modern instruments do not display raw photon counts. Instead, they measure the ratio fluorescence intensity divided by excitation source intensity. Advanced electronics continuously correct lamp fluctuations, process signals in real time, and displays spectra instantly. When selecting an instrument, you must consider your application. Simple fluorometers are cost effective, ideal for routine quantitative analysis used when concentration is known, whereas spectrofluorometers provide continuous spectral data, enable structural characterization essential for unknown molecules. Therefore, spectrofluorometers support both qualitative identification and precision quantitative measurements. Fluorescence is inherently inefficient. Much excitation energy is lost through non-radiative decay. Therefore, light source must be extremely powerful. A key rule is that fluorescence intensity is proportional to incident radiant power. Simple filter fluorometers often use low pressure mercury vapor lamps. These produce discrete emission lines, not a continuous spectrum. Common wavelengths includes 254 to 773 nanometers. Advanced spectrofluorometers use high pressure xenon arc lamps. These provide a smooth, intense continuum from about 300 to 1300 nanometers. They require powerful supplies and may operate in a pulse mode to achieve extremely high peak intensity. Modern systems increasingly use blue LEDs around 450 to 475 nanometer. They have tunable dye lasers, especially for microscopic samples or strict monochromatic excitation. After generating light, we must precisely control it and detect extremely weak signals. For wavelength selections, simple instruments use filters, advanced systems use precision grating monochromators. Because fluorescent signals are weak, ultra-sensitive detectors are required. The universal standard detector is photomultiplier tube or known as a PMT tube. In research systems, PMTs operate in photon counting mode, greatly improving signal to noise ratio. They are often thermoelectrically cooled, reducing thermal electron emission and minimizing dark current noise. And alternative technology, that is charge coupled devices known as CCDs. CCD arrays allow nearly instantaneous recording of an entire emission spectrum, especially useful in chromatography or fast flow experiments. Finally, we consider the geometry of the sample cell. The cells may be cylindrical or rectangular, constructed from optical glass or fused silica. What truly distinguishes fluorescence instrument is detector placement. Most measurements use right angle geometry. The detector sits at 90 degrees to the excitation beam. This is essential. If placed at 180 degrees, the intense excitation beam would overwhelm the faint fluorescence. The 90 degrees arrangement ensures the detector captures only the emitted light while minimizing scattered radiations. For opaque or highly absorbing samples, we use front surface geometry where fluorescence is collected from illuminated front surface. Proper handling is critical. Even fingerprint can fluoresce strongly under UV light, completely destroying the baseline data. Thank you very much for your attention. See you in the next lecture.